Assalamu alaikum. Today we are going to start lecture number 33 for the classical mechanics, that is previously related with the chapter we are studying about the kinematics of the rigid body. In this we are going to discuss about the angular momentum and the moment of inertia of a rigid body and how they are related to the work and power and the conservations of the angular momentum and how the inertia varies or when and how it remains conserved. That is the course for the BS 5th and course code is PHY 509. We are going to discuss about the angular properties of the for the rigid body which are rotational. In the kinematics we study the motion of the object which are in rotation as well as in the translational motion. We are going to start with the rotation of a rigid body. In this picture you can see different objects which are circular and spherical, and in the they can rotate, so these are the rigid bodies which have a rotation. So discussing about the rotation of a rigid body, moving to we're going to start with the thing that we are going to relate the parameters in the rotational motion with their corresponding quantities in the linear motion. We will write and use S is equal to r theta, that is the rotational displacement, and angular velocity will be v is equal to r omega, and rotational acceleration will be a is equal to r alpha, and the centripetal acceleration or the circular acceleration will be AC is equal to r omega square is equal to v square over r. And the C part, we can see use equations for the rotational motion with the constant angular acceleration. These are the equations we use for the rotational motion, that is omega is equal to omega naught plus alpha t, theta is equal to omega naught t plus 1 over 2 alpha t square, and the third is omega square is equal to omega naught square plus 2 alpha theta. These are the similar equations you have studied in the equations of motion, Newton's first law, Newton's equation of motion, first equation of motion, Newton's second equation of motion, and Newton's third equation of motion. Now starting the rotational kinematics. First of all we have to discuss about the angular displacement. It is defined as an angle through which a point or line has been rotated in a specified direction about a specified axis. The SI unit of the angular displacement is radian, that is designated as RAD. The figure shows the point P on a rotating compact disc CD moves through an arc length S on a circular path of radius r about a fixed axis through a point O that gives the angular displacement theta. In the figure you can see CD which have a reference line of O to the point that is sweeping along the in the counterclockwise direction. The arc made by the point to swept an angle theta is s, and the point distance from the point O to OP is the radius r in a circular path. Now from the figure, you can see that theta is equal to s over r, or s is equal to r theta, where theta is the angular displacement in radian, and s is equal to arc length, and r is equal to radius of the circle. The other units for the angular displacement is degree, and the revolution conversion from the revolution, that is the formula. One revolution is equal to 2 pi over radian, that is equal to 360 degree. You can convert from one revolution to degree, you can convert from one revolution to radian, or you can convert from degree to radian or revolution. The sign conventions of the angular displacement, uh, the rotational motion will be positive when it is in the anti-clockwise direction, and the negative if the rotational motion is in the clockwise direction. Now the other thing we are going to discuss is the angular velocity. Angular velocity omega average, it is defined as the rate of change of angular displacement, and the equation is given as omega average is equal to theta 2 minus theta 1 over t2 minus t1 is equal to del theta over del t, where theta 2 is the final angular displacement in radian, theta 1 is the initial angular displacement in radian, and del t is the time interval. Now the second thing, we can find the instantaneous angular velocity at any instant of time, that is omega. It is defined as the instantaneous rate of change of angular displacement, and the formula for that is given as, the equation is equal to limit, we substitute limit for the instantaneous, del t, limit del t approaches to 0 del theta over del t, that gives, if that limit is applied on that, that gives the complete change, that is d theta by dt, that is called the instantaneous angular velocity. It is a vector quantity. The unit of angular velocity is radian per second. The other unit is revolution per minute, rpm. The conversion factor for the velocity from one unit to other from the rpm is 1 rpm is equal to 2 pi over 60 radian per second, and that is equal to pi over 30 radian per second. Every part of a rotating rigid body has the same angular velocity, as every particle will move along with the direction of the body. Now to find out the direction of the angular velocity, it can be determined by using the right hand grip rule, where the erected thumb shows the direction of the angular velocity, and the curling of the finger shows the rotation of the direction of the rotation of the particles of the rigid body. These are the two figures that show the right hand grip rule for determining the direction of the angular velocity. The first shows the anti-clockwise direction rotation of the object. You can see by right hand the erected thumb shows the direction of angular velocity, and the curling of the finger shows the direction of rotation of the object. And in the second figure you can see that the erected thumb is in the downward direction and the object is moving in a clockwise direction, and the curling of the finger shows its rotation. So this means that it is in the clockwise direction, that it means that the rotation is in the clockwise direction with a negative sign. Angular acceleration, we are going to discuss about the angular acceleration after the angular velocity. First of all, we are going to discuss about the average angular acceleration, alpha average. This is defined as the rate of change of angular velocity. Similarly, like the average velocity, we are going to write the rate of change of angular velocity, that is alpha average is equal to omega 2 minus omega 1 over t2 minus t1. Omega 2 is the angular velocity, final angular velocity, and omega 1 will be the initial angular velocity divided by the angular uh, final time minus initial time, that is equal to del omega over del t. So where omega 2 is final angular velocity, omega 1 is initial angular velocity, and del t is the time interval. Now writing about the instantaneous angular acceleration alpha, similarly that previously we discussed, it is defined as the instantaneous rate of change of angular velocity, and the equation for that is written as alpha is equal to limit del t approaches to 0 del omega over del t, that is equal to d omega over dt. These all definitions you have already discussed in the previous classes and the previous semesters, but we are going to discuss about the rigid body kinematics and their rotation, so that is the necessary terms to be understood for the further discussion. Now moving to the next step, it is a vector quantity similar like the angular velocity. The unit of angular acceleration will be radian per second square. If the angular acceleration alpha is positive, then the angular velocity omega is increasing. If the angular acceleration alpha is negative, that means the angular velocity omega is decreasing. Now to find out the direction of the angular acceleration, if the rotation is speeding up, that means that alpha and omega are in the same direction as shown in the figure. It means that as the speed of the object rotation of the and the speed of the object rotating increases, it means the alpha is in the same direction as that of the velocity, angular velocity, and it will be in negative direction when the angular velocity is decreasing. Or you can say that if the speed of the object is decreasing, similar like a case of the rotating tires of a bus or a car. Not like that. If the rotation is slowing down, then alpha and omega have the opposite direction. You can see that in the figure 7.5, that the angular velocity is in the same direction as shown, but angular acceleration is in opposite direction. That means the object is slowing down. Relationship between the linear and rotational motion. At the Now we're going to discuss about the relationship between the linear and the rotational motion, and at the end of this topic portion of the chapter, students will be able to understand and relate the parameters uh, in rotational motion with their corresponding quantities in the linear motion. And we will write and use S is equal to r theta, V is equal to r omega, AR is equal to r alpha, and alpha is equal to r omega square is equal to V square over r. We are going to connect the linear and rotational motions and make a relationship between them. Relationship between the linear and the rotational motion. We're going to make a relationship between the linear velocity v and angular velocity omega. When a rigid body rotates about a rotational axis O, here you can see in the picture, every particle in the body moves in a circle as shown in the figure. That if we take an axis and a fixed point O, and that rigid body rotates, that means that every point or particle on that point will also rotate, as you can see from the figure. That is a fixed point O, that are the two axes, and that is the irregular shape of the rigid body, and that rigid body rotates in a circular path, and any point of P on the part with that rigid body will also rotate, making linear velocity uh, V, and making an arc S, and the angle swept angular displacement is theta, and that uh, length of the circular path from the O axis to the P point is radius r. That is the picture you can see here. From figure you can see that point P moves in a circle of radius r with the tangential velocity v, where its magnitude is given as As you can see from the figure that point P moves in a circle of radius r with the tangential velocity v. You know that the linear velocity v makes a tangent with the circular path. So where its magnitude is given at v is equal to ds over dt, and you know that s is equal to r theta. So when we substitute the value of s is equal to r theta, we get v is equal to r d theta by dt. And you know that angular rate of change of angular displacement gives us angular velocity, so we can write v is equal to r omega. The direction of the linear tangential velocity is always tangent to the circular path. You know that already. Every particle on the rigid body has the same angular speed or the magnitude of angular velocity, but the tangential velocity is not the same because the radius of the circle is r. Circle r is changing depend on the position of the particle. As every particle on the rigid body will have the same angular speed in the vertical direction of the along the fixed point of axis, but the tangential velocity is changing at every point as the radius r is changing its position at every instant of time, so that will not be the same. Now to make the relationship between the tangential acceleration at and the angular acceleration alpha, if the rigid body is gaining the angular speed, then the tangential velocity of the particle is also increasing. Thus, two components of the accelerations are occurred as shown in the figure. You can see a rigid body which have an irregular shape, and the from the center point where the object is hung from the center of mass to the point P, there the distance is called OP. From the point P, the centripetal acceleration is toward the center and the tangential acceleration is along the tangent. And if we add these tangential and centripetal acceleration, then by head to tail rule gives the resultant acceleration, that is a in the xy coordinate. uh, so we can find the magnitude of the resultant of the uh, sum of the tangential and centripetal acceleration. The components are tangential acceleration at and centripetal acceleration AC, that is given by at is equal to dv over dt, that is the rate of change of time velocity with time, and v is equal to r omega. If we substitute that value v is equal to r omega in the place of v, we get at is equal to r into d omega by dt. As we know that d omega by dt is the rate of change of angular velocity, so that gives the angular acceleration. So d, we replace d omega by dt with the alpha, so we can write 8 is equal to r alpha. But we know that the centripetal acceleration AC is equal to v square over r, and that is equal to r omega square. As we know that substituting the value of v, we get r omega, and cancelling one r with r, we get r omega square. Or you can say that by substituting the value of r, we get v is equal AC is equal to v omega. The vector sum of centripetal and tangential acceleration of a particle in a rotating body is the resultant linear acceleration A by head to tail rule. So we can write the sum of the two vector accelerations is A is equal to A tangential acceleration plus centripetal acceleration, that is the vector form. So we find out the magnitude of the resultant, that is A mod is equal to under root AT square plus AC square, tangential acceleration plus centripetal acceleration. Now the rotational motion with the uniform angular acceleration. At the end of that part of the chapter, the students will be able to write and use the equations for the rotational motion with the constant angular acceleration. We have three equation of motion in the angular form, that is omega is equal to omega naught plus alpha t, theta is equal to omega naught t plus 1 by 2 alpha t square, and omega square is equal to omega naught square plus 2 alpha theta. Here omega is the final velocity, omega naught is the initial velocity, theta is the angular displacement, alpha is the angular acceleration, and we have three equations of motion for the rotational motion. Now the rotational motion relation with the uniform angular acceleration, there are the symbols for the linear and rotational kinematics. That is, the linear motion has the displacement theta, this displacement designated in linear is s, and rotational motion is theta. The quantity initial velocity in linear motion is small u, and rotational motion is omega theta. Initial final velocity in linear motion is v, and in rotational motion that is designated by omega. Acceleration is designated by a in the linear motion and by alpha in the rotational motion, and time is same in the linear motion and rotational motion, that is the symbol t. Now the comparison between the linear and rotational motion with the constant acceleration. In the linear motion and the rotational motion, the linear acceleration and the angular acceleration are constant. The linear motion equation is v is equal to u plus at. The angular equation is omega is equal to omega naught plus alpha t. Linear motion second equation is s is equal to ut plus 1 over 2 at square. In rotational motion, the displacement is angular displacement is theta is equal to omega naught t plus 1 over 2 alpha t square, and linear motion equation for final velocity to find v square is equal to u square plus 2as, and for the rotational motion, that is omega square is equal to omega naught square plus 2 alpha theta, and in the linear motion the displacement is found out by s is equal to 1 over 2 v plus u into t, and in the rotational motion that is written as theta is equal to 1 over 2 into omega plus omega naught into t. And you know that angular displacement theta is has the units of the radian. Now moving to the next learning, that is the equilibrium of a uniform rigid body, which is also necessary to learn. For that we have to define and use torque, state and use the conditions of equilibrium for the rigid body, that is summation fx is equal to 0, summation fy is equal to 0, summation tau is equal to 0. We have some example problems in the next lecture. We have examples of the fireman ladder, wall, seesaw, pivoted suspended horizontal bar. There are the sign conventions for the moment of the torque, positive for the anti-clockwise torque and negative for the clockwise torque, that are opposite from the acceleration and velocity signs. The equilibrium of a rigid body. Non-concurrent forces are those forces whose lines of action do not pass through a single common point. The forces cause the rotational motion of as these two forces do not have a common point, so they give the rotational motion acting on the different directions. The combination of concurrent and non-concurrent forces causes the rolling motion on the body, translational and rotational motion. The figure shows an example of non-concurrent forces. You can see F1 and F2 are in the common point, but F4, 3 and 4 are not in the common point of F1 and F2. They are on the separate common point. So that means they are capable to rotate the object. To find out the torque or the moment of force tau, the magnitude of torque is defined as the product of force and its perpendicular distance from the line of action of force to the point of rotation axis. Tau is equal to Fd. Tau is equal where tau is the magnitude of torque, F is the magnitude of force, D is the perpendicular distance momentum. So because of D is equal to r sine theta, where r is the distance between the pivot point or the rotational axis and the point of application of force, so we can write tau is equal to rf sine theta, or tau is equal to r cross f. So we know that that is the cross product between the two vectors. Moment arm is also a vector quantity, and force is also a vector quantity. So sine theta means that they have the cross product. It means that the two cross products give a third resultant vector, that is the torque, where theta is the angle between force and the moment arm r. This shows that the torque is also a vector quantity. The dimensions of the torque are 2 tau dimension is equal to F mod into D mod is equal to ml square t minus 2. The unit of torque is Newton meter. Vector product, unlike the joule, unit of work also equal to the Newton meter, which is scalar product. It means that in the case of torque, the product is a vector product, so that is the vector quantity. But in the case of work done, the dot product between the two quantities is not a vector quantity, so it is a scalar quantity. So that is written in a scalar product, which is also Newton meter. Torque is occurred because of the turning or twisting effect of the forces on the body. Sign conventions of the torque are, if the turning tendency of the force is anti-clockwise, that is the positive, and if the turning tendency of the force is clockwise, that is the negative torque. So the value of torque depends on the rotational axis and the magnitude of the applied force. Now we have the first case, that is consider force in applied to a meter rule which is pivoted at one end, as shown in the figure 5.12b and 5.12b. You can see a ruler that is pivoted from one point, and the distance, the whole distance of the ruler is d. The force is applied in the upward direction, tau is equal to fd, that is the anti-clockwise direction. The distance of the from the pivoted point to the force, that makes an angle theta. D is equal to r sine theta, that gives the point of action of force at F, and tau is equal to Fd, that is F r sine theta in the anti-clockwise direction. uh, that is that F and D are in relation with the some angle theta. Case 2. Consider three forces are applied to the meter rule, which is pivoted at one end point O as shown in the figure 5.13. You can see that there is a force F1 making an angle theta 1 and F3 making an angle theta 2 with the distance from the pivoted point to the point for the force F2, that is theta 2, d2 is equal to r sin theta 2 and d1 is equal to r1 sin theta 1. So we have tau is 1 is equal to f1 d1, that is f1 r1 sin theta 1. Tau is equal to minus f2 d2, that is in the negative in the downward direction, so that is minus f2 r2 sin theta 2. Tau is equal to f3 d3 is equal to f3 tau r3 sin theta 3, that is equal to 0. There is no angle between the point of center of axis that is passing through the origin or the point of center of rotation. Therefore, the resultant of the all the torques is tau summation of tau naught is equal to tau 1 plus tau 2 plus tau 3, that is tau naught is equal to f1 d1 minus f2 d2. The caution, if the line of action of force is through the rotational axis, then the torque is 0. So tau is equal to rf sin theta will be theta is equal to 0. So tau will be 0. Now to find the equilibrium of the rigid body is defined as a body with a definite shape that doesn't change, so that the particles that compose it in fixed point position relative to one another, even though a force is exerted on it, there is a no change in the shape on the rigid body. If the rigid body is in equilibrium, means that the body is in the translational rotational equilibrium. All the particles will be in equilibrium, so there will be no translational change or the rotational change. There are the two conditions for the equilibrium of forces acting on the body. The first is the vector sum of all the forces acting on a rigid body must be 0. That means summation f is equal to f net is equal to 0. So it means that summation fx is equal to 0, summation fy is equal to 0, and summation f z is equal to 0. That means the forces present in all the direction x, y, z should be equal to 0. The vector sum of all external torques acting on a rigid body must be 0 about any rotational axis. That is the second condition, that is summation tau is equal to tau net is equal to 0. It means that the rotational forces are 0, so that means this ensures the rotational equilibrium. This is equivalent to the three independent scalar equations along in the directions of the coordinate axis. That means the torque in the x direction, summation tau x is equal to 0, torque in the y direction, summation tau y is equal to 0, and torque in the that direction, that is summation tau z is equal to 0. Now to find out the center of the gravity, where the that what is the center of the gravity, it is defined as the point at which the whole weight of the body may be concentrated or considered to act. So that is the point where if there are number of particles, then there must be a single point where the mass of all the particles, or the weight of all the particles is concentrated. So a force that exerts on the center of gravity of an object will cause a translational motion. It means that if there is the center of gravity, then if the object is exerted any force, then it produces a translational motion. The vector sum of all external torques acting on a rigid body must be 0 about any rotational axis. That is the second condition, that is summation tau is equal to tau net is equal to 0. It means that the rotational forces are zero, so that means this ensures the rotational equilibrium. This is equivalent to the three independent scalar equations along in the directions of the coordinate axis. That means the torque in the x direction, summation tau x is equal to 0, torque in the y direction, summation tau y is equal to 0, and torque in the that direction, that is summation tau z is equal to 0. Now to find out the center of the gravity, where the that what is the center of the gravity, it is defined as the point at which the whole weight of the body may be concentrated or considered to act. So that is the point where if there are number of particles, then there must be a single point where the mass of all the particles, or the weight of all the particles is concentrated. So a force that exerts on the center of gravity of an object will cause a translational motion. It means that if there is the center of gravity, then if the object is exerted any force, then it produces a translational motion. For the center of gravity, from the figure 5.14 and 15, that shows the center of gravity of a uniform symmetric object. The first is the rod and second is the sphere. The first rod refers to the midway point between the two ends, that is the whole length is of the rod is L, and the center point, that is the center of gravity, that is at the center of the whole length, that is from the center to the end point L by 2 on the left hand side, and from the center of gravity to the end point of the rod, that is L by 2 on the right hand side. Similarly, on the sphere, they refer to the geometric center of the sphere, where the from all the geometric sides, the center of gravity is at the center of the sphere. To solve the equilibrium of the rigid body problem, there are some strategies. The following procedure is recommended when dealing with the problems involving the equilibrium of rigid body. First, sketch a simple diagram of the system to help the conceptualize the problem. Number 2, sketch a separate free body diagram for each body. Number 3, choose a convenient coordinate axis for each body and construct a table to resolve the forces into their components and to determine the torque by each force. Number 4, apply the conditions for equilibrium of a rigid body. First is the summation fx is equal to 0 and summation fy is equal to 0, and the second is the summation tau is equal to 0. And at the end, solve the equation for the unknowns. These are the strategies used while the solving the problems related to the equilibrium of a rigid body. Now, for the rotational dynamics to understand, there must the one should be understand the center of mass. It is defined as the point at which the whole mass of the body may be considered to be concentrated. Its coordinates xcm icm is given by the expression below. Xcm is equal to summation I is equal to 1 to n mi xi over summation I is equal to 1 to n mi, and ycm is equal to summation I is equal to 1 to n mi yi over summation I is equal to 1 to n mi, where mi is the mass of the ith particle, xi is the x coordinate of the ith particle, and yi is the coordinate of the ith particle. These are the equations for the center of mass, for the y direction and the x coordinate. To find the moment of inertia, the figure shows the rigid body about a fixed axis O with the angular velocity omega. You can see a fixed point O along in the z direction, along which the body is rotating in with the angular velocity omega in the anti-clockwise direction. The mass points are m1, m2, m3, and so on mn on the rigid body. From the origin O to the m1, the position vector is r1. To m2, the from O to m2, the position vector is r2. From the center point O to m3, the position vector is r3, and so on till mn, the position vector from O to mn is rn. It is defined as the sum of product of the mass of each particle and the square of its respective distance from the axis of rotation, that is the position vector from the point O, is called the moment of inertia, as you can see in the figure depicted already. To understand the moment of inertia, For the moment of inertia, for the number of object particles for the rigid body, I is equal to m1 r1 square plus m2 r2 square plus m3 r3 square plus so on mn rn square, that is equal to summation I is equal to 1 to n mi square, where I is the moment of inertia of a body about a rotational axis, m is the mass of the particle, and r is the distance from the particle to the rotational axis. It is a scalar quantity. Moment of inertia in the rotational kinematics is analogous to the mass m in the linear kinematics. The dimensions of the moment of inertia is capital M L square. SI unit of the moment of inertia is kilogram meter square. The factors which affect the moment of inertia, capital I, of a rigid body are the mass of the body, the shape of the body, and the position of the rotation of the axis. These are the three factors that affect the inertia of the body, rigid body. The moment of inertia for the various bodies is also shown in the figure. The first is the hoop or ring and the cylindrical shell, thin cylindrical shell. You can see in the diagram the inertia for that is ICM is equal to M capital R square, capital M capital R square. Solid cylinder disc is given by the figure. You can see in the below that inertia for that solid cylinder or disc is ICM is equal to 1 over 2 capital M into capital R square. The moment of inertia of the various bodies shown in the table, where the number of objects about axis through the center of mass is written. The shape is the first shape is a uniform rod. You can see or long thin rod with the rotational axis through the center of mass of the length L, and from the center of mass you can see it is the rotation, angular rotation of the in the anticlockwise direction. For that, the inertial mass inertia is ICM is equal to 1 over 12 ml square, and for the solid sphere, that is, you can see from the diagram, that is inertia is ICM is equal to 2 over 5 mr square. This table shows the moment of inertia for a number of objects about axis. Here you can see a sphere, hollow sphere or a thin spherical shell. The diagram you can see is from the center of that sphere and have a radius r to the surface of the sphere, and the above angle arrow on the top and anticlockwise shows the angular velocity or the angular rotation of the object. And the equation for that hollow sphere or thin sphere inertia is ICM is equal to 2 over 3 mr square. Now, for the parallel axis theorem, that is called the Stirner's theorem, state that the moment of inertia I about any axis parallel to a distance d away from the axis through the center of mass ICM is given by I is equal to ICM plus md square, where I is the moment of inertia about a new axis, a new rotational axis. ICM is the moment of inertia about an axis through CM, means the center of mass. M is the mass of the rigid, capital M is the mass of the rigid body. Sum of the mass of the rigid body complete. Small d is the distance between the new axis and the original axis. Now, to find the torque for the rigid body, relationship between the torque tau and the angular acceleration alpha, consider a force F acting on a rigid body freely pivoted on an axis through the point O. As shown in the figure, you can see that there are a number of particles on the rigid body in a circular motion, and A1, A2, A3 are in the direction of the motion of the object, along with the velocity V1 is already in the along the direction of rotation. The force F is along the tangent in the anti-clockwise direction. The body rotates in the anti-clockwise direction, and a net torque is produced on the rigid body in the circular motion. A particle of mass m1 of distance r1 from the rotation axis O will experience a net force F1. The net force on this particle is F1 is equal to m1 a1 and a1 is equal to r1 alpha. F1 is equal to m1 r1 alpha. The torque on the mass m1 is tau1 is equal to r1 alpha F1 sin 90 degree, and that gives tau1 is equal to m1 r1 square. Substituting the value for F, that is m1 r1 square, that into alpha, The total net torque on the rigid body is given by summation tau is equal to m1 r1 square alpha plus m2 r2 square alpha plus so on plus mn on rn square alpha. So summation tau is equal to summation I is equal to 1 to 3 mi ri square into alpha, and we know that summation I is equal to 1 to n mi ri square is equal to inertia capital I. So summation tau is equal to I alpha, that is analogous to the force F is equal to ma, that is the rotational force. So tau is the rotational force, that is equal to rotational mass I into rotational acceleration alpha. From the equation of the net torque acting on the rigid body is proportional to the body's angular acceleration. So we can note that the net torque summation tau is equal to I alpha is analogous to the net force summation F is equal to ma, that is the Newton's second law. It means that these there here F is the linear force and tau is the rotational force. M is the linear mass and I is the rotational mass inertia, and A is the linear motion and alpha is the angular acceleration, but the two equations are analogous to each other. F is equal to ma is for the linear motion or the translation motion, and tau is equal to alpha is the equation of motion for the rotational motion of the object in the circular path. With the part of this of the lecture, the students will be able to understand in this chapter the solving the problems related to the rotational kinetic energy kr is equal to 1 over 2 I omega square, work is equal to tau theta for the rotational rigid body motion, and power p is equal to tau omega for the rotational rigid body. The rotational kinetic energy and the power rotational kinetic energy Kr. We consider a rigid body rotating about the axis OZ as shown in the figure. You can see the object is rotating along a z-axis from the pivoted point O. There are number of mass points m1, m2, m3 and so on, and every point mass m1, m2 has its own position vector. From the origin O to m1 is r1 with the velocity v1 in the direction of rotation, and similarly the v2 is also with the position vector r2. Mass m2 is with the velocity v2 with the position vector r2, and that is also in the direction of the rotation along the tangent. So similarly is the m3 and mn. Every particle in the body is in the circular motion about the point O, that is the rotational kinetic energy of the rigid body along the along one axis. The rigid body has a rotational kinetic energy, which is total of kinetic energy of all the particles in the body is given by Kr is equal to 1 over 2 m1 v1 square plus 1 over 2 m2 v2 square plus 1 over 2 m3 v3 square plus so on plus 1 over 2 mn vn square. Kr is equal to 1 over 2 m1 r1 square omega square plus 1 over 2 m2 r2 square omega square plus 1 over 2 m3 r3 square omega square plus so on plus 1 over 2 mn rn square omega square. Taking the common 1 over 2 omega square, we get Kr is equal to 1 over 2 omega square into m1 r1 square plus m2 r2 square plus m3 r3 square plus so on, that is plus mn rn square. So summing all the terms, we get Kr is equal to 1 over 2 omega square into summation I is equal to 1 to n miri square, and we know that summation I that inertia is I is equal to mr square. So for the sum of all the particles inertia term, that is summation I is equal to 1 to n miri square will be equal to capital I for all the particles. So we can write K rotational kinetic energy that is equal to 1 over 2 I omega square. From the formula of the translation kinetic energy KTR translational, that is KTR is equal to 1 over 2 mv square. After comparing the both equations, thus omega is analogous to V and capital I is analogous to linear mass m. For rolling body without slipping, the total kinetic energy of the body capital K is given by K is equal to K translational plus K rotational. K means the kinetic energy, so sum of two energies, kinetic energy translational and rotational, is equal to total kinetic energy, that where KTR is translational kinetic energy and KR is the rotational kinetic energy. Now the work. W. Consider tangential force Fx on a solid disk of radius r fully pivoted on the axis through the O as shown in the figure. You can see that the radius of that circular disk is solid disk is capital R, and the angle swept is d theta, and the arc made is ds. The force applied along the tangential path is for F, and the rotation is in the clockwise direction. The work done by the tangential force is given by dw is equal to F ds, and ds is equal to capital R d theta. So dw is equal to F R d theta. Integrating both sides, you get integral dw is equal to integral theta 1 to theta 2. Rf means torque, so we replace Rf with the tau, that is tau d theta, that gives w is equal to integral theta 1 to theta 2 tau d theta. If torque is constant, then W is equal to tau integral theta 1 to theta 2 d theta. Integrating and applying the limit, we have W is equal to tau into theta minus theta 1, that gives W is equal to T. W is equal to tau del theta, that is analogous to W is equal to Fs, where tau is the torque and del theta is the change in the angular displacement, and W is the work done. For the work, rotational kinetic energy theorem states that W work done, that is equal to rate of change of that is equal to change of kinetic energy. So we can write W is equal to del kr, where del r is the rotational kinetic energy, so that will be equal to rotational kinetic energy final minus rotational kinetic energy initial. Change between the two energies final and initial, that gives W is equal to 1 over 2 I omega square minus 1 over 2 I omega naught square. 1 over 2 I omega square is the rotational kinetic energy for the final form, and 1 over 2 I omega naught square is the rotational kinetic energy of the initial form. Now to define the power for the rigid body, the definition of the instantaneous power P is equal to dw over dt, where w is the work done and dw is equal to tau d theta. Substituting the value, we have P is equal to tau d theta by dt, and we know that d theta by dt is equal to omega, so we can write P is equal to tau omega. That is analogous to the power formula P is equal to Fv. Now the questions to be remembered are: the unit of the kinetic energy, work and power in the rotational kinematic is same as the unit in the translational kinematics. The kinetic energy, work and power have the same units for the translational and the rotational kinematics. Now the from that part of the chapter from the conservation of angular momentum, students will be able to use and define the formula of angular momentum L is equal to I omega, and state and use the principle of conservation of the angular momentum. The conservation of angular momentum capital L, it is defined as the product of angular velocity of a body and its moment of inertia about the rotational axis, or that is designated as capital L is equal to I omega, that is analogous to the linear momentum P is equal to mv, where capital L is the angular momentum and I is the moment of inertia of the body, and omega is the angular velocity of the body. We know that linear momentum is the vector quantity, so angular momentum is also the vector quantity. The dimension of the angular momentum is ml square t minus 1, and the SI unit of the angular momentum is similar like the linear momentum, that is kilogram meter square per second. The relationship between the angular momentum capital L with the linear momentum P is given by vector notation L is equal to R cross P is equal to R cross mv. Substituting the value of P, that gives R cross mv. The magnitude form of the angular momentum is L is equal to Rp sin theta is equal to mvr sin theta, and where r is the distance of the particle to the rotational axis and theta is the angle between r and v. From Newton's second law of motion in terms of the linear momentum, we know that summation F is equal to F net is equal to dp over dt, and hence we can write the Newton's second law in the form of angular form as summation tau is equal to rotational force, that is tau. So summation tau is equal to tau net is equal to dl over dt. In the place of linear momentum, we write the angular momentum, that is dl over dt, and states that the vector sum of all the torques acting on a rigid body is proportional to the rate of change of angular momentum. That is the definition for the angular momentum with the rotational force torque. Now, to understand the principle of conservation of angular momentum, it states that the total angular momentum of a system about and rotation axis is constant if no external torque is acting on the system. So that is written as I omega is equal to constant if summation tau is equal to 0. If it means that if the angular force torque is equal to 0, so that I omega will be constant. So we can write that summation tau is equal to dl over dt. It means that if torque is 0, then dl over dt is equal to 0. So integrating that we get dl is equal to 0, or dl is equal to summation l f minus summation li, and that means that initial angular momentum is equal to summation is equal to final angular momentum. That means summation li is equal to summation lf. It means that the angular momentum before and after is conserved. For there is a summary of the topic, that is linear motion velocity is v is equal to ds over dt. Relationship between the angular velocity is v is equal to r omega, and the rotational motion angular velocity is omega is equal to d theta by dt. And for the linear motion, the acceleration is dv over dt, and for the rotational motion, that is alpha is equal to d omega by dt. And the relationship between the linear acceleration and angular acceleration is a is equal to r alpha. The linear motion in linear motion, the mass is designated by small m, and in the rotational motion, the rotational mass is designated by inertia I, and the relationship between the inertia and the linear mass is given as I is equal to summation I is equal to 1 to n mi r I square. And for the linear motion, this Newton's second equation is summation f is equal to ma. In the rotational case, that is summation tau is equal to I alpha. And for the relationship between the force and the torque is given as tau is equal to rf sine theta. For the linear motion, momentum is equal to p is equal to mv, and for the rotational motion, angular momentum is l is equal to I omega, and the relationship between l and p is angular momentum and linear momentum is l is equal to rp sine theta. For the linear motion, work done is given as w is equal to fs, and for the rotational motion, work done is written as w is equal to tau theta. For the linear motion, pressure is p is equal to fv, and for the rotational motion, power is tau omega. These are the references for your classical mechanics. You can get help with this. Hopefully, the topic under central forces we have discussed is very understandable to you. If there is any kind of difficulty, you can ask me. Thank you. Is there any kind of difficulty? You can ask me the question. Hopefully, the whole topic with the starting with the central forces in classical mechanics is very understandable in the lecture. Thank you so much.